This video is about the application of Hess's law using enthalpy change of formation data. As a quick recap, let's remind ourselves what Hess's law states. Hess's law states that the enthalpy change in a chemical reaction is independent of the path taken. This means that as long as I'm starting with the same reactants and finishing with the same products, when I add up all of the individual enthalpy changes in whatever route I take, the total will always be the same. So if it's difficult to measure the enthalpy change of the direct reaction from reactants to products, I can find data that takes me on an alternative pathway, and when I add up those individual enthalpy changes, they will equal exactly the same thing. In this video, we'll consider how enthalpy change of formation data can be used to do exactly that. First off, it's important to know what enthalpy change of formation is. And the definition is the energy change when 1 mole of a substance is produced from its elements in their standard states. The key features of this definition, firstly, are forming 1 mole of that substance. Secondly, that we are producing it from the elements in that substance. And finally, those elements must be in their standard states. And by standard states, we mean the naturally occurring element at 100 kilopascals, and although temperature doesn't matter too much, we normally assume 298 Kelvin. So these are kind of room temperature and pressure conditions. Let's now consider a generic example. So in this generic reaction, I am trying to calculate the enthalpy change of that direct route. And to do so, I'm going to find an alternative pathway that involves using the enthalpy change of formation data. This means my alternative pathway is going to have to go via the elements in their standard states. The enthalpy change of formation data must be represented by arrows going from the elements in their standard states to form A, and to form B, and to form C, and to form D. So in this simple example, the enthalpy change of formation for my reactants would equal the enthalpy change of formation of A plus the enthalpy change of formation of B. And the enthalpy change of formation of my products is going to equal the enthalpy change of formation of C plus the value for D. And remember, if in my balanced equation I have, for example, 2 moles of D, then I would need to do 2 times the enthalpy change of formation of D. So, once I have this information, I can now calculate the enthalpy change of my direct reaction. To do so, let's consider the journey I would take from A and B via my alternative route to C and D. Firstly, I need to go backwards down that initial arrow. Because I'm going backwards, I simply need to change the sign of my enthalpy change of formation for the reactants in order to represent that reverse process. From that point, I then need to go up the next arrow to get from those elements in their standard states up to C and D. And in this case, because I'm going the same direction as the arrow representing the enthalpy change of formation, I simply need to add that value. I can now rearrange this general formula like this. So, whenever I'm asked to calculate the enthalpy change of a reaction using enthalpy change of formation data, I take the total enthalpy change of formation of my products and I subtract the total enthalpy change of formation of my reactants. and according to Hess's law, this will give me exactly the same value as the direct enthalpy change in my chemical reaction. Let's now summarise the key points. Firstly, Hess's law allows me to calculate the enthalpy change of a chemical reaction by taking an alternative pathway. One such pathway is using enthalpy change of formation data. And to do so, I need to calculate the total enthalpy change of formation of my products and subtract the enthalpy change of formation of my reactants. Hopefully this video was of some help.